Hi, this is a video that introduces the some basic physics of sound. I'm going to describe in a subsequent video slightly more specialized topics with sound, but this is simply very basic physics, kind of just what is sound. So sound, of course, it is a traveling wave, but in particular, traveling waves in the previous video, these water surface waves, so on the surface of water, like waves that surfers would surf, right, on the ocean, those waves were a disturbance of the flat surface of water by putting these ripples. So the ripples of the wave are the disturbance, and those ripples travel, right? So we say that's a traveling wave. But for a sound wave, the disturbance is quite different physically. And so, so the basic physics of sound is associated with how is a medium like air being disturbed. And the disturbance in particular is of the density of the medium. So the disturbance is on the density. And the way that you disturb the density is, for example, you take some, let's say, molecules of the medium. Let's say the medium is made out of these 9 molecules. So the way we're going to make a disturbance is we're going to look at the equilibrium situation. So this is the equilibrium situation. And to disturb the equilibrium, what we're going to do is change the density. That is, we're going to take some of the molecules and make them sit really close to each other. So let's say that I all of a sudden took a hammer and I struck this side of this object. Right after I hit it, a disturbance is going to show up and it's going to look like this. So I hit it on this side, and so these molecules get squeezed together in the direction that I hit it, but off to the right, these molecules haven't been disturbed yet, right? And if I wait just a small moment in time, the left side of my object is going to be able to expand back over to the left, but the middle of the object is now going to carry the disturbance over to the right side of the object. And so what the object is going to look like just a small amount of time later is like this instead. Can you see that that disturbance is in the density, that is the closeness of the molecules? The molecules are all sort of evenly distributed in the equilibrium situation, but a sudden hammer strike or a sudden compression somewhere can lead to a localized compression or a localized high density. And this is what sound is. So the medium, if the medium prefers to look like this right here, right, then it's going to try to restore itself to that equilibrium equilibrium distribution of the molecules. And so after being squeezed together, they're going to try to stretch back out. And that's how the wave gets moved along, is that the medium is trying to restore itself to what its equilibrium look is. Okay, so this is a disturbance of the density of our medium. And so what sound waves are is a bunch of compressions and rarefactions that travel along as a wave. So, so for example, right here, can you see this? This is a compression, and then next to it is a rarefaction. And then next to that is another compression, and then a rarefaction, and then a compression. But over in front of it, so let's say that this is the oscillator, and the sound waves, right? The waves are traveling away from the oscillator, taking energy away from the oscillator, out into the medium, right? And this location out here, right, is undisturbed. It's not disturbed yet, but the wave is coming. So this compression right here is going to travel in and be followed by a rarefaction. And then after the oscillator, let's say the oscillator gets turned off or it loses its energy finally, and it's no longer oscillating, then this wave that traveled through will keep on going, heading out to the right, taking the energy way out to infinity. And what's left behind is just equilibrium air, right? Equilibrium molecules distributed out into a uniform density, no longer a disturbance. But the disturbance actually kept on going, and it just keeps on going because that energy needs to go somewhere. So these waves, the way that we'll characterize the wavelength is by looking at the distance, that is distance, say, in meters or centimeters or miles even, between adjacent compressions, for example, or even adjacent rarefactions, the centers of them or something like that. But that's what the wavelength is, right? The velocity, it sort of goes without saying, but you could say that the velocity of our wave is the speed at which a single compression in the wave is traveling, right? So that's called the wave speed. And then there is this other thing that we can describe about a wave called the periodicity. And so it's just like how I described it with water waves in the previous video. You pick a fixed location in space, and you count the number of seconds it takes for between, say, one compression going by and the next compression going by the same place. And that's called a period. And then the frequency of the wave is simply just 1 over the period and can be described in hertz, which is the 1 over the second per second, right? Okay, so sound can travel through a medium that has a density, where the molecules have a preferred relative spacing relative to each other, right? So the molecules don't like to be too close and they don't like to be too far away. When they're too close to each other, we say that's too high in energy, and when they're too far apart, that's also too high in energy. So there's some minimum energy equilibrium separation between molecules in our medium, in our material. So since solids can be made out of these particles, liquids can be made out of these particles, and gases can be made out of the particles, sound can travel amongst or in any of these media. And actually sound travels with different speeds in solids, liquids, and gases. And more than that, for example, sound travels faster, say in diamond, than through glass, even though both are solids and both feel very rigid. So the way that we tend to use sound when we talk to each other or listen to music is when sound is traveling through a gas, right, which is just the atmospheric air. So sound can travel through solids, liquids, and gases, and that's a really important thing to realize. Sound doesn't just travel through air. Another thing that's very interesting is sound waves are longitudinal. The disturbance that goes along with what we call a sound wave is these compressions and rarefactions, which is, so in this example that we're looking at up here, the sound wave is traveling from the left towards the right because the oscillator is on the left side and the medium is on the right side of the oscillator. So we're watching sound waves travel towards the right. You can see the velocity vector is pointing towards the right, right? So that's the direction our disturbance is traveling. But if you look, our molecules, they are only moving side to side, right? Left and right, for this distribution of the molecules to change. The molecules are not moving transverse to the velocity. So since the molecules are moving in the same direction as the velocity, the sound wave is considered a longitudinal disturbance. Yeah. Cool. So here's another interesting detail. In air, down near the surface of the earth with our, the air pressure has a certain value at the surface of the earth, and the air pressure is less the higher up in the atmosphere you go. But down near the surface of the earth, at roughly room temperature, some comfortable human temperature, the velocity of sound, the speed of sound is 340 meters per second, roughly. Some people say it's 343 meters per second. But yeah, so this is the speed of sound that's typical for how humans listen to sound, right? This is also the Mach number, what's called the Mach number. So there are airplanes that are called supersonic airplanes. So sonic refers to sound, and super means more than. So these are airplanes that fly faster than the speed of sound. If an airplane flies at Mach 2, Mach 2 means 2 times the speed of sound, 340 meters per second. So that's a very fast object, right? Mach 2. Really quickly, before I forget, there is no sound in a vacuum. In vacuum of space. Because, and the reason is because there is no medium, right? Empty space, the vacuum of space, like out in the middle of space, far away from the Earth and the Moon, there is no atmosphere. And even though there are little particles of dust, essentially, and small things, they are very, very far apart from each other. So if you cause one of them to move to the side, it's not likely to hit anything because the density of the vacuum of space is so low. So there is no way for an oscillator to lose its energy by sending sound out into empty space, because empty space quite literally will not push back on the oscillator. The empty space cannot push with a force and do any negative work on the oscillator, removing any energy from it. Okay, so here are some examples of oscillators. An example that maybe all humans at this point are used to is speakers, right? You might have earbuds you listen to podcasts on, or music, right? Or you have headphones, or you just have a stereo system in your car with speaker heads. And these speakers, what I mean by that is a lot like what I drew up here. So a speaker head's like a cone that can push and pull on air. So that is, it's airtight, right? Air can't travel through the cone, through the surface of the cone. So when the cone pushes outwards, it bunches up and compresses air. And then when the cone pulls backwards, it rarefies the air. It sort of spreads the air particles out, right? So if you do that with some frequency, then you'll create a sound wave of that frequency on the air traveling away from the speaker. Another example is a bell. So a bell often has this kind of a shape, and it's, so if you hit this bell with a hammer, then what you do is for a really short amount of time, you cause a little sort of like deformation of the metal in the bell. But the bell, is this rigid thing, and if you don't break the bell with a hammer, you just deform it slightly. The bell's elasticity causes the bell to be an oscillator, right? And so this bell oscillates. So the walls of the bell push out and pull backwards on the air surrounding the bell. And so what travels away are these sound waves. All right, so sound. And so if you don't continue to ring the bell, you just hit the bell once. So you set the bell into oscillation. Sound is traveling away from the bell, but what sound is doing is taking energy away from the bell. And so the bell gets quieter and quieter and quieter until the bell no longer oscillates. But if you took this bell out into space and you rang it, it wouldn't produce any sound and it would continue to oscillate. A guitar is another interesting example. So a guitar is interesting because it's actually more than just the guitar strings. So a guitar has a shape that kind of looks like this. And if you take a string on the guitar and you pluck the string actually has a transverse wave that travels along it. But what that vibrating string does is it distorts what's called the resonator box of the guitar, right? This is an acoustic guitar, non-electric. So the string is vibrating the walls of the resonator box, which is causing the air inside the box to get high pressure and low pressure, which sends sound away from the box. And the sound is of the same frequency as the vibration frequency of the guitar string. And vocal cords actually operate in a really similar way. So an interesting thing to point out is eardrums are quite literally little tiny flat pieces of thin skin. And when sound waves come up, what they do is they push and they pull, right? So this is a compression and a rarefaction. And the rarefaction is just hitting the eardrum, followed by another rarefaction, right? Low density, followed by a really high density. And so the high density pushes inwards on the eardrum and the rarefaction pulls outwards on the eardrum. And the eardrum has a nerve line that goes to your brain that can tell you, that your eardrum is vibrating in and out. And so this eardrum is also an oscillator, and this oscillator is being energized or oscillated by being pushed on and pulled by the sound wave that hits it, right? So this is a very real sense of the sound wave bringing energy and adding energy to the oscillator called the eardrum, right? So this is a transference of energy. The way we tend to keep track of information is by paying attention to the frequency of the sound. We're listening for the sound frequency to change, right? And that's how we convey information. A little bit of information is also conveyed in the volume, right? The loudness. You might know that your mom is mad at you if she raises her voice, for example, right? So that's a conveyance of information. So frequency is something that you're used to, but what about amplitude, right? So amplitude for sound amplitude is loudness, right? And amplitude is also the density change from equilibrium. That is, the harder you push and pull, for example, with a speaker head, then the larger is the density disturbance, right? And when that gets, for example, to your eardrum, if the density disturbance is very, very large, then your eardrum gets pushed inwards and pulled outwards very, very hard. And your brain can detect that as a loudness. It understands that as a loudness. If the sound is too loud, then quite literally the density variation can rip or destroy your eardrum, right? And so that's because the forces involved cause your eardrum to deform too much, right? It's just like tearing your skin because you push on your skin too hard, right? So your eardrum is a very sensitive, very, very lightweight, very thin piece of skin. Yeah, so you have to protect your hearing. Okay, so that's the basic physics of sound.